this. Oh, okay. All right. Okay. So good afternoon, everybody. What I'll be talking today is actually of the evolution of a mixed state in a strongly disordered superconductor. And what I will show is that the evolution of the mixed state here is very different from what we are normally used to in terms of normal proliferation of abricos of vortices. So this work was done mostly by the students and postdocs. The samples was grown by these two gentlemen along with my colleague, Thami Javel. And the theoretical simulation that I will show were done by Amit Ghoshal and Anurag Banerjee in another institute called Indian Institute of Science, Education and Research. Okay, the toy that I will be using mostly for this work is this millikelvin scanning tunneling microscope. This is a home-built scanning tunneling microscope. It goes down to 350 millikelvin. We can apply a field up to 9 Tesla. And here it's connected with a sample deposition chamber. So all data that I will show you are on pristine surface, whether they are thin films or crystals. Crystals are cleaved, and thin films are grown in situ and transferred in the STM for measurement. More details about this setup you can find in this paper. So before I show you disordered sample, let me show you what we get in usual samples, and that we get what we expect. So this is a pure niobium diselenide crystal, and here we get a vortex lattice. If we do a spectroscopy along this line going to the center of the vortex core, we see that at the center of the vortex core we have this bound state, and if we go now to slightly dirtier sample where we have cobalt dope, we have put a small amount of cobalt doping in niobium diselenide. We again have this vortex lattice, but here at the center of the vortex core, you don't see this bound state anymore. This bound state is very delicate, so here it gets mirrored, and you get a flat normal region at the vortex core. If you increase magnetic field, of course, you have more and more vortices that get in, and eventually, at some point, these vortex cores will overlap, and you lose superconductivity. So this I have talked in the last vortex workshop. This is, for example, another example of an amorphous molybdenum germanium film with a TC of 30, with a thickness of 30 nanometer. Again, you see roughly very similar feature. You have here again, you have a normal vortex core without the bound state. As you increase field, you can image these vortices up to 7 Tesla, and beyond 7 Tesla, you reach HC2. So the vortex lattice constant, if you measure it from the Fourier transform, it follows the usual expected behavior. Now, I come to the actual system that I will be telling you about. So we will be using niobium nitride, and this niobium nitride, when we started synthesizing, we realized that we can synthesize in epitaxial form on magnesium oxide substrate. We also realized that this system, we can control the disorder from sort of conventional state to a situation where it is very strongly disordered. So as you increase the disorder, you have the TC that comes down, and you have the resistance that goes up, and eventually you get an insulating-like behavior. So the disorder here is in the form of niobium vacancy. This I would like to stress. It's not nitrogen vacancy. It's niobium vacancies here. And we have measured many, many samples over 5 years. So the cleanest sample that we can get has a KFL of about 10. And this is the most ordered sample with a TC of about 17 Kelvin. And as we go to more and more disordered sample, the TC comes down. And around KFL1, we don't have any TC down to 300 millikelvin. The normal state conductivity also crashes around the same level of disorder. Okay, before I go to the vortex state, let me quickly give you an overview of the zero field state. So if you take a niobium nitride, which is disordered, but not very disordered, so it's at 9 Kelvin, that's about here. Then you do this STM at various points, let's say along a line. You see that you have a more or less uniform gap. If you look at the coherence peak height, there is some variation, and this is what I am plotting here. You have regions where the coherence peak height is high and regions where it is slightly lower. Nevertheless, the coherence peak is present everywhere. And more importantly, if you now take the average spectra over this 200 nanometer by 200 nanometer region and fit it with BCS, you see that the gap actually decreases in a BCS fashion, and it goes to zero exactly where resistance appears. So this is conventional BCS behavior. There is no puzzle here. But suppose now you take a sample which is much more strongly disordered, 2.9 Kelvin. Now if you do this spectroscopy at various points, you see that at some points in the spectrum you see a coherence peak. At some point you see a gap-like feature, not a complete gap, but the coherence peak is completely gone. Whenever you have this coherence peak which is completely gone, you also see that the zero bias conductance is slightly higher. And if you now take this average of this coherence peak at positive and negative bias and make a map, you see that you form this kind of an inhomogeneous state where these blue regions are the regions where the superconducting order parameter measured by this coherence peak height is completely suppressed, and these regions where it is finite. You also see an inverse correlation with the zero bias conductance. So if you make a zero bias conductance map, wherever it's blue here, it becomes red and so on. The real surprise is, however, here. Now I take this entire area, this 200 nanometer by 200 nanometer area, and I plot here, I color code the conductance. So this blue region is the gap. And I plot this spectra as a function of temperature. What I observe is this. Here I have superposed the resistance variation with temperature. And you see now that the superconducting gap disappearing has nothing to do with TC. TC is here, but the superconducting gap keeps on persisting up to a much higher temperature, which we call as T star, and that's well above TC. In fact, this is what we call the pseudogapped state in this material. And in fact, you realize that the gap here is an irrelevant parameter, because you take these three samples which vary, the TC varies by a factor of 2, yet you see that the gap is roughly the same for all of them, about 1 milli-electron volt. So therefore, now you can do this measurement on many, many samples. And if you plot TC and T star, this is what you get. With increasing disorder, TC comes down, and here TC goes to 0. At low disorder, you have TC and T star which are the same, which is the BCS regime. But as you go to stronger disorder, for samples below 6K, this T star tends to saturate here, and you have a pseudogap region here where you have a signature of a gap in the electronic density of states, but no zero resistance. So we believe that this is a region where you have a phase disordered situation. So this transition, we know now that gap is not a relevant parameter. We think that what is driving this superconducting transition is actually phase disordering. Further evidence of that can be obtained if you actually calculate the superfluid stiffness. And the superfluid stiffness you can estimate from the penetration depth and coherence length. So we measured the penetration depth for each of these films using a two-coil mutual inductance technique. And then when we convert this into the superfluid stiffness and the gap scale here, we see this. For low disordered sample, as expected, the superfluid stiffness is at least one order of magnitude higher. So this is phase fluctuation is an irrelevant energy scale. But as you go to stronger and stronger disorder, you have this J which comes down and in fact becomes smaller than delta. So therefore, if you are in this shaded region, here phase fluctuations are important. And if you are deep inside here, you will have a phase disordering transition for superconductivity before you have the Cooper pairs that disappear from the system. So our physical picture was the following, that you have these islands of superconductivity, which are actually Josephson coupled by these regions which behave like insulators. And at TC, you have these islands which become phase incoherent. As you go to higher temperature, you have further fragmentation and so on. Okay, now let me come to the main topic of this talk. I take this sample now, which is 9 Kelvin TC. Here you don't have a pseudo gap, and however, you have some variation in the coherence peak heights. So the superconducting order parameter is not completely uniform. And I look at the mixed state. So here, first of all, you don't see anything that looks like a regular vortex. And you have these patches, however, and if what I have put here as dots is the minima. This is the conductance map close to the, at a bias close to the coherence peak. And this minima, if you associate with vortices, then of course you have a sort of very disordered vortex pattern like this. Now, if you look carefully, it appears as if these vortices are forming a sort of nucleating along these lines like this. And it's effectively segregating the superconductor into these patches which don't have too many vortices. And these patches are isolated from each other by these lines of vortices. The other interesting feature that we observe is that these, I'm showing you representative data, but we have done many, many line scans along these points that we identify as vortices. And what we observe is that away from the core and at the center of the core, we always have this gap-like feature. There is an increase in the zero bias density of states at the center of the vortex core. And at the center of the vortex core, the coherence peak seems almost completely suppressed. Nevertheless, we never observe a normal vortex core where the conductance is flat, or the density of states is flat. Now, these vortices, I showed you, they form these lines which seems to segregate the which seems to fragment the superconducting state. To look at this more carefully, we have measured the full conductance over this 32 cross 32 matrix in this area. And this is at H equal to 0. If you look at the zero bias conductance, it's essentially uniform and close to 0 everywhere. But this zero bias conductance, now it starts forming long tails. You have a large variation as you apply magnetic field. And this is the distribution of the zero bias conductance. And regions where this zero bias conductance is higher correspond to the region where you have the vortices. You see an anti-correlation here between this map and this map, which is the coherence peak height. So wherever the zero bias conductance is high, your coherence peak height is also suppressed. Now, to make sense, we, along with our colleagues, we did some numerical simulation. So using this attractive Hubbard model, we solved it with Bogoliubov-Dozhen. And here you have the regular kinetic energy and the attractive interaction here. And the disorder is simulated in the chemical potential by putting this term Vi, which is site dependent. So you choose it from a random number within a particular range. So first, for the clean case, if you do this simulation, just to show that we get what is usual, you have, let's say, in the clean case, you put one vortex here, and you observe that at the center of the vortex, you have this bound state. Away from the vortex core, you have this kind of a gap. Now, let's see what you get when you put in disorder. So for disorder, we choose a value of disorder strength which roughly corresponds to what we have in our experiment, which means that in zero field, the density of states is BCS-like, as we have in our experimental sample. And if we plot the coherence peak height map over this area of simulation, we see again that the coherence peak height is finite everywhere, but it has this variation. So it forms this patchy structure. Now we put, this is a snapshot, we have a lot more of the simulation, but here we have put 4 vortices here. You can see these vortices from the phase map, here, 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 and here. And this is the zero bias conductance when you have these vortices. So as expected, the zero bias conductance is slightly higher wherever you have the vortex center, and it's lower elsewhere. This is the coherence peak height map. Since these are finite simulations, they are relatively noisy. If you do a cross correlation between these two, you will see that there is an inverse correlation, but it's not completely apparent from this picture. But more importantly, this is what you get for the local density of states away from the vortex core and at the center of the vortex core. At the center of the vortex core, just like we see in our experiment, there is a soft gap still persisting. Now, this is from simulation. The physical understanding that we have is the following, that normally for an Abrikosov vortex, you have this circulating supercurrent around the vortex which goes as 1 by r. And at one point, this kinetic energy of the Cooper pair exceeds 2 delta. So therefore, you have a core which becomes normal. Now, in this case, we know that if you have lower superfluid density at some points, then the relevant energy scale for destruction of superconductivity may not be delta, but J. So possibly what happens here is we increase the kinetic energy as 1 by r, and when it reaches J, then you have the phase coherence that is lost. So you get a core region which is essentially pseudogap, which has paired objects but is incoherent. Now, if that is the case, then you can see that in the presence of field, the superconducting state becomes very much like a strong disordered state. Though I have started with a superconductor which doesn't show a pseudogap, which seemed roughly BCS-like, it was a 9 Kelvin TC film, but in the presence of disorder, I have this emergent granularity, field-induced granularity, which is coming in. If that's the case, then when I increase temperature, there should be phase fluctuation, thermal phase fluctuation between these domains, which are separated by these lines of vortices, and I should observe the pseudogap. And this is exactly what happens. In zero field, of course, I don't have a pseudogap, but as I keep applying the field, Tc and T star starts diverging, and this divergence becomes larger and larger. So if I plot on a phase diagram, this is my HC2 or Tc line, or TCH line, and this is the T star, and in between these two, I have this pseudogap state. Okay, so just to show you that the pseudogap state is not caused by local variations of Tc, I take 2 regions. Here is where I have a vortex, and here is where I don't have a vortex. And I look at the temperature dependence of these two regions. So one of them has a very well-formed coherence peak. The other one, the coherence peak, is almost suppressed. And if I look at the zero bias conductance as a function of temperature, I see that the zero bias conductance becomes 1 exactly at the same temperature, which is T star. So this is not local variation of Tc. Now, I'll just give you in 2 minutes a brief view of another sample now, which is strongly disordered already. So now I take a sample which is here, which has a Tc of 1.65 Kelvin. Here, even in zero field, I have a strong pseudogapped state. And this is how the RT are in magnetic field. But more interestingly, if I do a RH at various temperature from 300 milli-K to 3.5 K, I see that there is this universal crossing point. So above this, you have a negative temperature coefficient of resistance. Here you have a opposite. Here you have a positive temperature coefficient of resistance, so it's insulator-like. Here you have a negative temperature coefficient of resistance. It's a superconductor-like. It's not in the strong disorder regime where we see really the superconductor-insulator transition in a very clear way, but nevertheless there is this separatrix in terms of a universal field. Now here, if we look at these conductance maps, it becomes extremely disordered. Maybe these patches are vortices, but we cannot identify them very clearly anymore. But if I now look at this spatially averaged density of states as a function of temperature, this is what I see. Here, for example, this is in zero field. I already have a Tc and a T star. I keep increasing field. Tc keeps on coming down. T star roughly hovers around the same temperature. And for example, at 8.5 Tesla, here, this is the RT. There is no hint of Tc anymore. It's just, the resistance is just going up, but I still have the T star, which roughly remains at the same temperature. So if I plot now the phase diagram, this is how it looks. T star is almost field independent, at least up to 9 Tesla. But here, this is the HC2 line. These are two different criteria that we have used. But the HC2 line is here. So the superconducting state is here. And you have this huge pseudogapped state that emerges, that remains here. And here it extends all the way down to t equal to 0. Okay, I am done. So the summary is that with application of magnetic field, the superconducting state, in the presence of this strong disorder, it gets progressively fragmented into domains. And these domains are separated by these lines of vortices, which completely suppresses the local order parameter wherever they are. And we observe a field-induced pseudogapped state that progressively widens with magnetic field. So in a way, increasing disorder is identical, phenomenologically at least, to increasing magnetic field. This is not such a new thing. There are people who know this from transport measurement. So for example, there are many groups who have this kind of data. This is from Dan Chahar's group, where you take an indium oxide film, and what you see is that this film is superconducting in zero field, but as you apply field, it becomes insulating here. And actually, it becomes very strongly insulating. So it looks as if when you are in the strong disorder regime already, increasing field and increasing disorder has actually the same effect. And I think we have got a clue of why we have the same effect, because microscopically the state evolves in a very similar fashion. Thank you.
Thank you.